Question 2 from the 2022 Advanced Higher Physics Examinations from the SQA. A merry-go-round at a fun fair rotates about an axis through its centre. And for part A, it says the merry-go-round accelerates uniformly from rest. It takes 18 seconds to reach the angular velocity of 0.52 radians per second. And for 3 marks, we have to calculate the angular acceleration of the merry-go-round in this time. Well, we look up our data sheet. We know that the final angular velocity omega is equal to the initial angular velocity plus the angular acceleration times t. Very much similar to the equation we have in the linear kinematics, v equals u plus at. Now, we've got the following data. We know that the initial angular velocity is going to be equal to 0 because it's going from rest. The final angular velocity is 0.52 radians per second. We don't know the angular acceleration, so we have to put a question mark there, but we do know that the time for this to take place was 18 seconds. So all we have to do is rearrange this to get what alpha is, and a quick rearrangement gives you angular acceleration alpha equals omega minus omega naught divided by t, and therefore alpha is going to be equal to the final angular velocity, 0.52, take away 0, put a bracket around there, and divide that by t, the time, which is 18 seconds. So alpha comes out to be the following. If you do that in your calculator, you get 0.0288. We'll round this up so that alpha is going to become 0.029 to 2 significant figures, and the units will be radians per second every second. So that's the first one. Angular acceleration comes out to be 0.029 radians per second every second. 2a part 2. Calculate the angular displacement of the merry-go-round in this particular time for 3 marks. We know the angular displacement theta is related, if you look at the relationship sheet, is equal to omega naught t, the initial angular velocity times t, plus 1/2 alpha times t squared. And once again, that's very similar to the displacement we have, s equals ut plus 1/2 at squared for linear kinematics. So let's see what we've got here then in our little data bank. We asked to find theta. That's what we'll try and find. And we know that omega naught is going to equal to 0 because it's starting from rest. And we know that time t, that was the value which we had to begin with, is 18 seconds for this particular change in velocity. And we know that alpha, we just worked that out, is equal to 0.029 radians per second every second. So we've got theta, omega naught t, and alpha. So just plug the things into the equation and we should have the following. The angular displacement theta, put a bracket around this, omega naught times t, well, it's going to be 0 because the initial omega naught is going to be 0, plus 1/2, put a bracket around this, 1/2 times 0.029, and don't forget to square the time squared, 18 squared. So we put our answer for that, theta, into a calculator and we get out an answer of 4.698, and of course the angular displacement will be measured in radians. Now we can make that into our significant figures. We've been using 2 significant figures so far, so we'll use 4.698 will become 4.7 to 2 significant figures radians, and that will be the angular displacement. Question 2 continued, part B. 2 students, X and Y, ride on the merry-go-round. The students are sitting on adjacent horses as shown in figure 2a. You're looking down on the merry-go-round from the top of it. Now, part I is the following. It says, explain why student Y has a greater tangential velocity than student X. Well, we know that the tangential velocity v is going to equal to omega times r, the distance you are from the centre. And if you rearrange that, you can see that we're going to have v divided by r is going to equal to omega. Now, omega remains a constant. The angular velocity of that rotating merry-go-round is always the same. So therefore, we have the situation here. Vx divided by the radius, which x is away, rx say, must be the same as Vy divided by the radius of y from the centre. You can picture it like this here. There's x there's the radius from it, and that's x's tangential velocity, Vx there. Now, because the radius of y is bigger, to keep the same ratio, then it must be that Vy must be bigger. So if the radius here, Ry, is bigger, if Ry is larger than Rx, which you can see there, than Rx, then it follows that Vy, in order to keep the same ratio, it must mean that Vy must be greater than the Vx. So the tangential velocity of y will be greater than the tangential velocity of x, simply because it has to the same ratio in order to keep the angular velocity constant. Remember, omega here is always the constant. Part 2. State whether the centripetal acceleration of student y is greater than or equal to or less than the centripetal acceleration of student x. And you must justify your answer to give you your 2 full marks. The centripetal acceleration A is equal to the tangential velocity v squared divided by r. And we know that v, the tangential velocity, is equal to omega r. So we can swap that v squared to become omega squared r squared divided by r, and one of the r's cancel out, and therefore we're left with the centripetal acceleration is equal to omega squared times r. So v, the acceleration, equals omega squared times r. The centripetal acceleration A is going to be equal to omega squared and times r. And we use the same argument we used in the previous question, because we know that omega squared must be a constant. The angular velocity for x and y must be the same. So therefore, we must have omega squared, we rearrange, equal to the acceleration divided by r. So if we increase r, then we have to increase the angular, the centripetal acceleration must increase also. So centripetal acceleration A, centripetal acceleration A must also increase, because the common thing here is that the angular velocity must remain the same for both x and y, or any position on that rotating disc, which we call the merry-go-round. So if you're a further distance from the centre, to keep the same angular velocity, you must have a bigger centripetal acceleration. So the centripetal acceleration, in fact, will increase the further you go out from the centre.